looks like we got a good connection today. Also looks like we got almost half the class here. Okay, no, not yet. Yes, okay. Good deal. All right, so do we have any questions? Thank you, guys. So is the audio's coming through okay? All right, I don't see any questions. So I guess we'll go ahead and get started. Real quick update. We are here at the end of the semester. And we're actually at one class behind. For Wednesday, it should be everybody should upload their report as it is. Design reviews. So to answer that question, I'll give you some more detail. I'll probably give you, till Monday the 14th is a week from today. I'll probably allow you guys a couple of extra days to turn it in. If you want, I want to make sure that I can go through them and assign grades with enough time. But as far as the full report, for every design review, you need a presentation, and you need the report as it is. Okay. So you can work under the assumption that you need to turn everything in with the final report, and I'll give you a take-home test that you can have, but I'll probably allow you as much time as I give you for the take-home test to also finish the report. I'll try to give you as much time as I can. Is homework 6 the last homework? Yeah, so if you see the screen here, these problems are all the last ones that are due. So you'll turn in these problems on Wednesday with the design review, and then if you need until, I'd like to get the homework in because I don't want to grade. I don't want to have the TA grade all the homeworks and then start to grade the tests and the report on the same time. So chapter 15 homework, we haven't finished the second lecture of chapter 15, which I still owe you guys. So I will probably give you until Monday to turn in that, and so you have a chance to watch the last lecture. So I still owe you one lecture. I will upload. I'll give you more time for the homework because I'm a day behind, so sorry about that. But I'll make sure that you have enough time to watch the video and turn it in. Yes, I will delete it. So I think what we did is we combined two homeworks and I just made them both due earlier in the semester. So pretty soon you guys are going to be getting course feedback. So please fill out the course surveys and just be honest about the things you thought were good about the class and the things you thought were bad and things that I can do better. Believe it or not, I do read every comment, and there's always one or two people that help me understand all the ways that things could have been better. So I read those comments as well. And then I try to incorporate those into my next class. So your feedback matters to me. So I would appreciate you getting in. And if you did have a good experience or a better than average experience, that also helps me too, because I do care what you think, and I do care that you learn, and I do care that you have a good experience. And I do want to do better, every semester. And I'm usually aware of a lot of different ways that I can make it better. The entire homework group or just chapter 15? Well, chapter 11. I'll make them both do the same time. I mean, because it's at the end of the semester and everybody has a lot of stuff going on. I know probably some of you are graduating as well. So you're trying to find jobs and find places to live and all that stuff. So, we can be flexible with the dates. The main thing is I want you to do it, and I want you to at least have the experience. So, if you get into trouble too, you can email me, and if I can give you more time, I will. But try to turn it in. I'll update the due dates on Canvas, but do try to turn it in. So in general, I've been pretty happy with this class. I know that some of the open-ended design problems are a little bit frustrating. I also know that having a semester-long design project in this environment is also frustrating, but I think you guys have really done a good job. I've been pretty happy with everything. I do want you to provide all the detail in your final reports. Some of your reports were lacking in putting it all together, and I really would like to see it complete, if not perfect, at least complete. So where you do your analysis and equations, make sure you show all your work. And try to make the report kind of like more of a narrative where you kind of put everything together. I think if you follow the guidelines for the report, you'll do fine. Also, the last test is only going to be something that will incorporate power screws, fasteners, and bearings, and maybe something on springs or things that you haven't had before, and it shouldn't take you. I'm going to design it to be something that will reinforce your learning, but hopefully not waste too much of your time. All right. So if there's any other questions, just throw them in the chat. I'll try to keep my eye on it. Otherwise, we'll just go ahead and get started here with today's lecture. All right, so today we're talking about screws and fasteners. And although they probably don't come across as one of the more interesting machine design concepts, they're arguably one of the more important concepts, because if you get this wrong, you can create a disaster. There are thousands and thousands of fasteners for all sorts of different applications, specialty applications. As a designer, you really do have a lot of freedom when it comes to creating a joint using a fastener. Boeing 747 has 2.5 million fasteners. It's a huge part of the economy. Many mechanical engineers spend their lives and their careers working in companies that produce fasteners or sell fasteners or install fasteners, or make machines to automatically fasten things. And so today we'll talk at a pretty high level of bolts, screws, and nuts, and as they relate to machine design. This is a picture here that captures quite a few different types of nuts and bolts and washers. And you can see there for all sorts of different applications. Some have gaskets to prevent water. Some are split washers to prevent backing out. Some are self-tapping screws. Some are bolts. And then obviously you can see in here there's a lot of different types of different materials. These are anchors. And obviously we're not going to talk about all of these. And we're not going to talk about rivets and bonding because we're out of time. But I did upload the lectures on rivets and bonding. They're kind of slow and long, and they don't have so many pictures because I had a little bit different format, which I found was a little bit painful for everybody. But those lectures are on there, and there's good content and good material. I took the PE, and they did have bonding on there. They do also have concepts that we'll discuss with the fasteners and preloaded bolts. And they will have... So these concepts are concepts that, if you have time or you can make time, I encourage you to at least finish the other components of the machine design that we didn't go over. All right, so let's talk about screw terminology. The screw shape is actually a mathematical shape, and it's if you have a helix that runs along an axis, okay? That's a screw shape, and this helix wraps around the screw axis, so that when you turn the screw, it advances it in a linear fashion. So it's a way of us translating rotary to linear motion, and it's one of the most common ways of fastening two objects together and creating a joint. Now, if you go back in time, there are some different, there's a history of the terminology. And so this is from like one of my old lectures here, but basically back in the day you had UNC, which is Unified Coarse Thread. It's now, some people call it UTS or Unified Thread Standard, and then you have UNF, which is Unified Fine. It was previously the USS or the United States Standard, and this was previously the SAE Standard or Society of Automotive Engineers. This has all been encapsulated in the UTS now, and Norton in his book calls this UNS, Unified National Standard. Okay, and then we have the ISO standard. So in the book he calls it UNS. People also call it UTS, but it encompasses the former USS, United States Standard, and the SAE standard. So those are encapsulated here, and then we have the ISO threads. So they have the same thread geometry, whereas they have this 60-degree helical pitch, and they have the minor pitch and major diameters that are defined based on the pitch. And so these are standard. We'll show another slide about that in a second. When you rotate the screw, it will advance according to the lead. Okay, and if you have a single lead screw, it'll advance the pitch because the pitch and the lead are identical. If you have a multi-threaded screw or a multi-start screw, then the lead, which is the amount that the screw will advance with a single rotation. When you go one revolution, the lead is how far your linear advance is, and that's the number of starts or the number of threads for a multi-threaded screw times the pitch. Okay, and pitch you can measure between the two teeth. It's not always obvious if they're multi-start or not. Over here is a drawing that I sketched, which is a little bit sloppy, but this is single versus double threaded. So if you're looking at the bottom of the screw, this is where the thread starts. Okay, and the helix goes around here, This is your thread, and this is your pitch. So your lead and your pitch are the same in a single threaded screw. So as you go around, you'll advance the pitch. Over here, you have a multi-start double threaded screw or multi-start screw. So you have threads that start two different places. So what that means is you have a helical angle that's defined by this, that wraps around this distance. But because you have two starts, you actually have they're interlaced with each other, and so the pitch is half the lead. Okay. So in that case, when you rotate, you advance, you ramp up this whole helix, and you're going to advance the lead. But in this case, the lead is twice the pitch. Okay. And then I know this is new terminology. It's pretty simple. But so most screws, almost all screws, are single start screws. Power steering screws, on the other hand, they have, I think, up to 5 leads. But in general, it's usually one lead, and then you have specialty applications where there's 2 or 3. So this is just a picture here of the standards it's taken from Wikipedia. They have a nice little standard geometry here for the threads, and the threads are the same for ISO and US standards. So all of these geometrical parameters are the same. The only difference is in the metric system we use millimeters to define this thread geometry, and we use inches in the US standard. Okay. This is how a bolt would be called out, or a screw would be called out. This is a 1/4-20 bolt. That means it's a 1/4 inch diameter. It has 20 threads per inch. And that's the biggest difference between the US and ISO standards. Okay, so this is defined in threads per inch. And over here, this is the pitch diameter. Okay, and this is a coarse pitch diameter. So if I have a 1/4-20, and then I have this UNC, so this is the unified thread, and it's the coarse thread. Okay, and this 2 is the class. It's a class 2 thread. That means it's we'll talk about the classes in a second. So it's a class 2 thread, and it has an A here, which means that it's an external diameter thread. If it had a B, it would be an internal diameter thread. When we go below a 1/4 inch, okay, so if you see down here on this table, all right, we go below a 1/4 inch, then we get into these numbers. Okay, and then we can talk about a number 0 to a number 12. And there's a formula to find the number, or the diameter, major diameter, which is the outer threads diameter of a screw. And that's 6 times 0.013 plus 60. Okay, so that's how we get these numbers. So if you look here, for number 6 screw, it's 138 thousandths of an inch. And that's what you would get if you multiplied the screw number 6 times 13 thousandths and then added 60 thousandths. All right. So if you've ever been to Lowe's or Home Depot and you've been looking for a bolt or screw, and then you see the 12s and the 1/4 inch right next to each other and they look about the same, it can be a little bit confusing. But these are just the standards. And so as you can see, even Wikipedia uses UNC, unified coarse, unified fine, and unified extra fine is the other one. Okay, so the extra fine, if you need extra fine threads, you can find those there. And these are the geometries of the screw, and you can see that the geometries of the geometry of the screw is defined in terms of the pitch, or you can find the height of the thread in terms of the pitch. And this is what they use to make them. Those are the geometries that you make them. Class 1 threads are loose fit. for easy assembly, or for dirty environments. They have a lower tolerance, so they're looser when you screw them in. They're hardware quality screws and bolts, for around the house or for applications where, you're just trying to put stuff together, but you don't necessarily need high performance. Lower tolerances always lead to less cost, so they're cheaper. Class 2 threads are what's called free fit. They're the most commonly used for general machine applications. Okay, so likely you're going to be using Class 2. Class 3 are medium fit, and they're used for closer tolerance, higher quality applications. So if it really matters that the threads are really, really close to each other when you screw them in, then you do that. The benefit of that is if you have loading on a higher class thread, then more threads will likely be engaged and picked up by that load. Class 4 fit is obsolete, and Class 5 fit is an interference fit. Okay, so the threads actually interfere with each other. And an example of that would be an automotive leaf spring shackle bolt. So these can be interference fits, so that when they're bolted on, they interfere with each other, so they can stay put and not vibrate out when you go down the road. So when we talk about fasteners with standard threads, we need to eventually calculate the area that loads are going to be transmitted over. And in that case, we have a choice. We can use the outer diameter minus the inner diameter, the pitch diameter, the radial diameter, and kind of get an estimate of what portion of the bolt area is actually going to be stressed if we have a tensile load. Okay, so this is if we have a bolt and we have a load that's pulling against the bolt. What area does that bolt act over? Okay, and obviously it's going to be picked up by this inner diameter, and it turns out, but we also have material out here, and it turns out that the most accurate way of representing it is to use this area here, which is the area including the threads, and it's just the pitch diameter plus the minor diameter here. So it's just the average of these two diameters. So it's a little bit outside of this minor diameter, and it's just that area that of that average of that diameter times pi over 4. Okay, so for UNS threads, the pitch diameter is the same. For ISO threads, the minor diameter is a little bit different, and it's defined here. And this N is the number of threads per inch. Okay, P is the pitch distance. Okay, so once we calculate that, we can find the tensile stress that a bolt experiences due to an applied load F. These are the standard unified thread standards and the ISO thread standards for most of the sizes up to 4 inches. These are the coarse threads, these are the fine threads, and they went ahead and calculated the tensile area here that you would get if you applied a load. This is the area that load would be applied over. And you have your coarse and fine. Keep in mind there's also the extra fine, but the table's not shown here. All right. So a little bit of a terminology, some points on terminology here. So screws and bolts, obviously they hold things together as fasteners. Screws are driven or they're rotated into a thread. Okay, the thread could be on a bolt or into a tapped hole. Power screws or lead screws are screws with a higher load thread design, and those are used to move loads. So they do not follow, they are not the standard screw threads according to the ISO or UTS or UNS threads. They're defined differently for power screws. So what's the difference between a screw and a bolt? Okay, so there's people that have strong opinions about this, and it's good to know when you have a when you have a screw and when you have a bolt. But effectively, a screw becomes a bolt when they're used with a nut. Okay, so when a bolt is threaded into a tapped hole, it becomes a machine screw or cap screw. Okay, not of cap screw, it should be or cap screw. So when a bolt is threaded into a tapped hole, it becomes a machine screw because it's used as a screw, because screws are rotated into a thread. Now, a bolt says, ANSI says that a bolt is intended to be held stationary while the nut is torqued onto it to form a joint. Screws are intended to be turned into a part, either a threaded hole, untapped hole, or no hole in the case of self-tapping screws. Okay? So if you have something that goes through a hole, it's a through hole, and you're putting a nut on it, it's a bolt. Okay? If you're screwing it into a hole or a or fixed nut or whatever, then it's a screw. So it has to do with whether or not the the fastener that you're inserting it is held stationary when it's assembled. If it's held stationary, it's a bolt. If it has to be turned into the joint, then it is a screw. So let's talk about power screws. So power screws have a different defined geometry for their threads. And we have square thread, Acme thread, buttress thread, and there's a couple of other threads. The most common is the Acme thread, okay, because it's a little bit easier to make than the buttress. The buttress or square threads. And they move material. They have more material for the thread. So here you can see the pitch width is P/2. If you go back to the standard here for the standard screw, you have an area here that's P/8, and P/2 is actually over here in the middle of that thread. Okay, so there's less material. You look here, you have P/2, also at the middle of the thread, but you have more material. Okay, because it doesn't go up to a point. So that helps to capture more of the load. Power screws are used in precision machine tools. They're used as screw jacks for your automobile to jack up your car. They're awesome because you can transmit super high loads with very, very simple mechanism. They're used in crawl spaces and building applications to jack up floors. And so, a person with a power screw jack, this little device can, introduce a significant force and really compact package. If you think about CNC machine tools, they have type of power screw. They have lead screws, and the lead screw is threaded. These are shown are ball screws. There's actually balls here that rotate in these races, and they're a type of power screw, and these are used often with servo motors to do precision motion control, and we'll talk a little bit more about those. We often need to know how much torque, if we're designing an application that's going to have a power screw, how much torque do we need to apply, and what is our load that we can lift, and we need to know and make sure that it's not going to automatically back down and drive the nut if we let go of it, because that would be a problem. All right. So we have the two scenarios here. This is a cross section of a screw thread climbing up the ramp of a nut. Okay, and if we're going up, we have friction that's opposing the motion, and if we go down, we have friction that's opposing the motion. And so we have these cases where we're lifting and lowering. We have to have two different equations that describe that. If we take these square threads, and the square threads are these guys right here, we'll start with that case. If we have the square threads, we'll treat this like a square thread, and then we can balance the sum of the forces in x and y to 0, get an expression for the force required to lift it up, and an expression for the normal force. We can eliminate the normal force between these two equations, and we can find the force necessary to lift up a screw that has this applied load P. And it's in terms of this angle lambda. This is the lead angle of that thread. And it's in terms of the lead over pi dp, where dp is the pitch diameter. Okay. So then this is the force. If we multiply the force times the pitch diameter radius, then we can get an expression for the torque required to lift it up. Okay, we just multiply it by dp over 2. That's F times R. If we want, we can use this equation here for lambda and get rid of these sine and cosine terms by dividing it by the cosine. And using this expression, tangent of lambda is the sine of lambda over the cosine of lambda. And we can get rid of the sine and cosine terms, and we can get this expression here. We also have to consider this torque here. That's the torque of the collar, okay? And that's the torque right here at this interface. And this one has a bearing, so it would be the torque in these bearings required that you also have to overcome to lift this load. The torque that you apply, sometimes you have a bearing, you don't necessarily have a thrust bearing. You can have it just riding on two surfaces, and obviously if you did that, you'd have a higher collar coefficient of friction. Okay. So this, if we put it all together and we say, well, we have this torque which is required to lift the load, and we have to add this collar torque, then the torque to lift the load up is just the sum of those two torques, where we just take this guy and add the collar torque, and we get an expression for the overall torque. So we can go through the same analysis. We change the signs here for the friction force. And if we do that and follow it through, that we get this equation right here, where these signs are changed for the lead, okay, and this friction term here. It's the only things that change. Now, this is for the power screws. It's sort of just like this is the physics of it. If we have Acme threads going, this is Acme threads. This is lifting. This is U is up, D is down. Then we have these two equations here, and the difference in the Acme thread is we have this lead angle lambda, but then we also have this angle alpha, which comes from this thread geometry here. Okay, so when it runs up the ramp, we have to resolve those forces and consider that taper as well, and that taper is this angle alpha. Okay, so these are the equations that we'd use for lifting and lowering a load in terms of an Acme thread, okay, which is probably the most commonly used, and this is for a square thread. So if they have oil lubricated interfaces, okay, so they, when you put them in service or whatever, you've oiled them, then the friction coefficient that you can use for these equations is 0.15 plus or minus 0.05. Okay, that's everything you need to know to calculate the torque. And notice that these calculations are based upon the geometry of the screw. Okay, so you can actually go look up in a table of standard Acme threads. You can get your pitch diameter, your lead, your angle alpha for that Acme thread, which is 14.5 as a standard. Then you can plug those in. You can estimate the friction in the collar. the friction between the thread and the nut, which is 0.15 plus or minus 0.05. And then this collar friction is going to be whatever friction you have here. So if you have a plain bearing where you have a surface on a surface, it's obviously going to be higher. If you have a thrust bearing, it's going to be lower. If you have a needle bearing versus a ball bearing, then you can have a little bit different friction calculations based upon what we learned last lecture. Now, you do not want your screw to be back driven. Okay, so you cannot have a load back drive the screw, right? Especially if you use your screw jack to lift up your car and you are crazy and don't put a jack stand under there to protect yourself. You wouldn't want that screw to back out when you're underneath it. So the requirement is that you have to have the friction condition that prevents back driving has to be met. For an Acme thread, the friction has to be greater than or equal to the lead over pi dp times the cosine of alpha. If you have a square thread, then the friction has to be the lead over pi dp. Okay. Back driving is actually desired for some applications. I don't know if you've ever been to your grandfather's shop or seen something like this. It's called a Yankee screwdriver, and the working principle of this is you have a very coarse thread on here, very long lead angle, and that that changes the slope that it has to ramp up and down. So if you apply a load, it actually spins this. Okay, this is the old school drill. So then you can put different bits in here, and the way that you work it is you will push this on an axis, and it'll cause it to rotate one direction. Then you pull it apart and push it, and then you can drill holes or drive screws that way. All right. Friction requirement is for static loading only. Okay, so these equations, this is just if nothing is moving or vibrating. Okay, if you have vibration, the screw will work its way down the ramp. Okay, so vibration causes screws to back out every time. Okay, you have to assume that if you have any vibration, that anything you design, that vibration will cause those bolts to fall off, and you've got to deal with it. So you deal with it with lock washers, lock nuts, thread lock, and other things, and cotter pins or whatever. But you have to deal with vibration, because when you have vibration, bolts will back out. When we talk about power screws, they have an associated efficiency, and efficiency is just the power in, okay, divided by the power out. Okay, so this is torque times distance, and in this case, this is 2 pi radians, so it's T theta, and that's force times distance, and that distance is the energy required to go around one full revolution. Okay, so that's your input power if you're applying a torque to get it to go around one full revolution. What comes out is the load, and that load is lifted by the lead, because the lead is how far it goes up in one revolution. So we can look at the ratio of the output power to the input power, and that's the efficiency of the power screw. And as you might expect, because we have such high friction, the efficiency is pretty low. So if we ignore the collar friction, then we can get an expression for the efficiency like this, or we can use the expression for the angle lambda, or if alpha is 0 in the case of square threads, okay, then you have this expression over here. So all the cosine alpha becomes 1, and then you get this expression here because the angle alpha is 0. So this is your square thread efficiency. This is your Acme thread efficiency. So this is a plot of the efficiency versus lead angle for different friction coefficients. Okay, usually we're down here. Okay, for a standard Acme thread with a coefficient about 0.15, and that's what we found. If we had an oiled thread to nut surface, this is what it would look like. All right, so if we had a 1/2 inch, 10 threads per inch Acme screw with a 4-degree lead angle, we're actually down here. Okay, and we have a 34% 34% efficiency, so it's pretty low efficiency. So you can get much greater efficiency and much less friction if you use a ball screw. Ball screws are much more expensive, but you can dramatically reduce the friction. Okay, the way that these work is there's a train of balls, so as it rotates, these balls are free to go around the surface and make their way all the way back and create a ball train. And these have these spherical balls, and then they have grooves that can hold the spherical balls. They're more expensive because it takes more energy to make them. They have to be ground and hardened. But this is what you're going to find in a lot of precision machine tools for precision motion applications. Back driving is a big problem because you have such low friction. You can push these pretty easily and get them to move. So they require a brake. They have really high load capacity because the load's picked up by all these balls, which are deeper in the grooves, okay, which is typically larger than the conventional screw. And they don't suffer from stick slip, where you have this initial sticking friction that you have to overcome that you get in lead screws or power screws. These are used in all sorts of applications, such as aircraft control surfaces, landing gear actuators, machine tool axis. This is what you'll see in your CNC machine, automotive steering mechanism, hospital bed mechanisms, and you name it. There are a lot of places, but they are expensive. All right, so here's an example of just how do we calculate that. So the question is, what is the lifting power? What is the lifting and lowering torques and the efficiency of the power screw? Shown in the figure. It's the one we showed in the previous figure. Using an Acme screw and nut, and they want to know if is it self-locking. In other words, can it be back driven with the load? What's the contribution of the collar friction versus the screw friction if the collar has sliding friction or rolling friction? The screw is a single start Acme thread, 1 1/4 5, so it's 1 1/4 inch, 5 threads per inch. The axial load is 1,000 pounds. The mean collar diameter is 1.75 inches, and the screw and nut are lubricated with oil. Sliding friction is 0.15. Rolling friction is 0.02. So we have to compute the lifting and lowering torques. Okay, one with the sliding collar and one with the ball bearing collar. Okay, and that's this. The ball bearing is a 0.02, sliding is 0.15. And so we do both of those. We use the up calculation. In this case, the lead is equal to the pitch because we have single start. So we basically just plug the numbers in from that standard, and we get that the torque required to lift it up is 253 pounds. I said, note that the collar friction actually exceeds the screw friction. Okay, so that means this term here, due to the collar right here, this second term here, this collar friction, is actually higher than the screw friction. It's pretty interesting, and that's why they're so inefficient. The torque to lower the load is found from the same equation where we said we change the sign here and here versus here and here. Okay, and then we can just plug those numbers in. Obviously, we should get less torque required to go down because weight is helping us out. All right, and our collar friction is obviously going to be the same. So we can look at the efficiency, the output over the input power. We do this. This is 0.26. For just the screw. If we add the collar friction, the efficiency drops to half of that, to 0.13. So they say recalculate the collar torque and lifting torque if we have the ball bearing. Okay, so with this lower friction, 0.02. Okay, So then this will be a lot less, 17.5 pounds versus 131 pounds. Okay, when we plug all those numbers in, with this thrust-bearing washer between the two, we find that the efficiency is 0.23%. 0.23 versus 0.13. So it's almost the efficiency of the screw. Then we need to check and make sure that it can't be back driven. So we just plug the geometry in for that lathe screw and the friction coefficient. Okay, and this works out to be 0.06, and the 0.15 is about a little over twice that, so it self-locks. So that's pretty much it for that you will see for power screws. There's different types, like we had the buttress type, and there's even more types of power screws. If you're going only in one direction, the load only goes in one direction, you can have specialty screws, but this is enough for this class for now. So the next thing we need to talk about, so are there any questions before we go further? So are y'all still with me? Any questions? So the next thing we need to talk about is the stress in the threads, because when we design a fastener, we need to know how many fasteners we need for a given application, and we do that based upon the loads that we think we're going to experience. We need to make sure that the threads aren't going to strip out. Okay, and threads, there's threads, the number of threads and engagements, kind of like the number of teeth and gear engagement. The more we have, the more distributed the load is. So ideally, we'd have multiple threads engaged, so that load is picked up by more of the material. The worst case is that if you have a single thread pair that takes the load, and the best case is that all of the threads share the load. The reality is actually closer to a single pair taking the load. And what's important to note is if you have a ductile material that is not super hard, and you apply a load, then there's some play in it so that it can actually deform, not necessarily permanently deform, but deflect. And if it's allowed to deflect, like in a softer material, then more threads can pick up that load as that bolt or nut deflects. Usually the nuts are softer than the screws, and so if they have local yielding, then that causes them to have a greater contact area. In the case of power screws, they have hardened shafts, usually hardened nuts. They yield very little because they're more brittle, so you're going to have less threads that are engaged. Okay, so we can calculate the axial, tensile, and compressive stresses from the tensile area from the standard bolt tables. This is what we calculated earlier just by looking at calculating AT. Power screws, it can experience both compressive and buckling loads versus most other screw applications where you put a screw and the screw is loaded in tension. If you have a power screw, the load, you can move the power screw back and forth, and that screw changes from from tension to compression, or compression to tension, and you just have to make sure then that you can't buckle. Okay, so you have to design against buckling if you're using a power screw. So the way we calculate the shear stress in the threads for the screw or the nut, either one of them can shear because the nut is usually weaker. It usually shears first. If the nut shears first, it shears at its major diameter, okay, because we're defining it from the beginning, the inside. If the screw shears first, it shears at its minor diameter. Okay, if the materials have equal strength, then the bolt may shear at the pit. Then the bolts may shear at the pitch diameter, or the nut may shear at the pitch diameter. Okay, so it's hard to predict exactly what will happen if you have the similar materials. And since the number of threads can actually vary based on the material, what we do to calculate the stress is we just express the stress as a function of the number of threads that are in there. So we express the stresses as a single thread. So then if we make assumptions about how many threads are engaged, then we can increase the amount of area that's taken up by that load, and we do that. So depending on the type of bolt we have these factors here. Okay, these are the area factors. This is the inside area factor and outside area factor, or minor and major area factors. We have to use the major diameter if we're talking about a nut. We have to use a minor diameter if we're talking about the screw. So if we want to calculate the shear area, so we can get the shear stress either in the nut or the tapped thread or the screw, we just have to make sure we're picking the right geometry factors. Now, this table tells us what the area factors are, okay, for different types. So if we have a standard thread, okay, UTS, UNS, or ISO thread, then the minor factor is 0.8 or 0.88. If we have square threads, it's 0.5. If we have Acme threads, it's 0.77. If we have buttress threads, it's 0.90. Okay, so you can see here that the design of these different threads gives you this different amounts of area that are in contact with it. And then we can use these parameters and calculate the shear stress in those threads. Okay. So now the question is, well, how many threads do we need to have engaged in a fastening application? Okay. Well, if your nut is long enough, then the load that's required to strip the nut will exceed the load required to shear the screw threads. Okay. If your nut is even longer, then the load required will be the load that's necessary to cause the screw or bolt to fail in tension. So we can calculate the minimum nut length to prevent shearing from the threads for any screw size. Okay, and the failure mode will actually be the failure of the screw in tension. So we solve for that, the number of threads that would be sufficient such that the screw itself would fail. Okay. For UNS, ISO, or Acme threads, we have this lengthen. It's called the strip length, and it has to be greater than the tensile strength. So when the diameter is less than an inch, then the nut length has to be half the diameter or longer. And if it is, then if you have a load, then the load required to strip the threads is going to be greater than the screw's tensile strength. If the diameter is greater than 1, then the nut length has to be at least 60% of the diameter to exceed the screw's tensile strength. When you have tapped holes, you need a little bit longer thread engagement for tapped holes versus nuts. Okay, and so if you have the same material, like steel on steel, which is the most common case, then the thread engagement has to have at least the diameter. Okay, so if you have the same materials, the thread engagement or the distance that the threads are engaged has to be equal to the diameter. So if you have a 1/4 bolt, then you need a 1/4 inch thread engagement so that you have that minimum length, and then you're getting the full material strength for pull out for that full bolt. If you have a combination of materials, you get a little bit different ratios. So if you have a steel screw in cast iron, bronze, or brass, then the thread engagement is 1.5 the diameter. If you have a steel screw in aluminum, you have a thread engagement that's twice the diameter of the screw. Okay. When you tighten screws down, they are going to experience a torsional stress. Okay. At the screw nut interface. Okay, if you have well lubricated surfaces, it causes the nut to actually experience most of the torsional stress. If you have rusty surfaces and rusty interface, it causes the screw to experience most of the stress. And that's like if you've ever worked on your car, like a water pump that on an older vehicle that's all rusted out, it's very common that bolt will fracture when you're trying to remove it, and then you have to use a screw extractor and use colorful language and spend hours and go back to the store, borrow a screw extractor from your friend, and hope those don't break. So this has caused many people, rusty bolts and engine blocks has caused many people lots of grief. If you have power screws, if the collar has low friction, the torsional stress is picked up by the screw. Okay, the limiting case really for all these is that all of the torque is picked up by the screw at the minor diameter. And so we can say, well, that's the worst case scenario. So when we calculate the shear stress, we can just use the applied torque and then use the minor diameter of the screw to calculate the torsional stress that's experienced by that screw. Now, fasteners are classified by either their intended use, their thread type, or their head style. Okay, and we saw this earlier that if we have a fastener here and we put a bolt on the end, if we keep this is intended to be stationary, this is intended to be threaded on, then this is a bolt. Okay, if we don't have the bolt and we're going to put it into a threaded hole, then this becomes a machine screw. In this case, it's a cap screw. This is a stud. So studs you might see in your engine head, where this part will be threaded in. This is usually like a higher tolerance part that goes into the material, and then this would be like a different class thread. And they do that so when you try to remove it, you can take the nuts off of this, the nut off this surface easily without backing out the whole stud. Okay. So if we classify them on thread types, we can have tapping, self-tapping, thread forming, and thread cutting. And these are the different geometries that you'd see. Okay, so these are thread forming and thread cutting screws. And they have different geometries based upon the material you're going into, the intended application to cut into the material and make threads as they go in. These are just some examples. This is a self-drilling versus a self-tapping screw. So this is the front side, that's the back side. So as you go in, this is tapping the hole and threading the hole. And this is actually drilling a hole and then picking up the, then threading these threads into the material in the hole. Okay. So these are very useful fasteners for a lot of different applications. Okay. Another way of classifying it is according to their head style. Okay, so these are socket head cap screws. These have Allen wrench tops on them, so they're usually hardened steel. They go in all sorts of machine applications. Here's a shoulder screw, so you can actually use this as a pivot. So it has a shoulder material here, so you can work out your gap sizes so that you can actually use screws like this as pivots. And then we have tons of slotted small machine screws, which you see everywhere, you know, slotted screw or Phillips screw. And these are just lower strength screws that you'll find in all sorts of different, you know, applications everywhere for like lower load applications. And these cap screws are these commonly used in machine tool applications. These are more like consumer products in general. And then we have all sorts of different nuts and washers. As we said earlier, vibration is our enemy, and we have to deal with vibration and expect that if we have vibration that the screws will back themselves off because it's a ramp. And if you have vibrational energy, the nut will work its way off the screw. And to prevent that, we can use different types of hardware. These are some examples. This is an elliptical lock nut. In this case, you have a material here that's designed to interfere with the thread. Okay, so as you go through, this actually smashes up against the thread. And that'll help prevent it from going off. Nylon nuts are also very common. So when you thread it through, you actually are threading through solid nylon. That nylon wraps around the threads and allows you to get it on, but also prevents it from backing off very easily. Then you have this pin lock nut. As you go through, this pin is bent back and it's pushed against the thread, and it's intended to keep it on. Then you have this flange lock nut here, which will dig into the material when you put it on and deform that material because of these sharp edges and try to create a better interface. So then another application is to put two nuts on the same screw. So you put one nut on the screw and then you'll run the other nut onto it to create prevent it from backing off. There's hex nuts. These are designs, you put them in. These are often found on automotive wheels. And then there's a hole through the shaft, and you put a cotter pin through there to prevent that from backing off. And then you have acorn nuts. These are mainly for decorative purposes. And then you have wing nuts, so you can put them on with your fingers. And then we have different types of washers that'll kind of dig into the metal and try to prevent it from coming off. In general, these lock washers, okay, are less effective than the lock nuts, okay, in general. And then we have these SEM nuts, which is just a combination of nut and captive lock washer. So as you put it on, the teeth will kind of dig into the material and help prevent it from backing off, even if you have vibration. All right. Now, this is a pretty important slide. Threads for really large diameter screws are often cut by using a screw machine, Swiss machine, or lathe. Well, for larger, it won't be a Swiss machine, but you have a screw machine or a larger lathe to cut threads in outer diameter. When you do that, you have this grain geometry here that's pretty uniform, and it's not necessarily adding to the strength of the material. And so if you need threads that can withstand higher loads, then you can use rolled threads. Okay, and the rolled threads are where you take a material and you put it through a thread roller, okay, and it rolls the threads in. In this case, this is an Acme screw. I think this is just a standard fine screw. And so you have these really hard dies, and they come in, they push against the thread axis, and then they roll the threads in. There's no cutting of material. So that if you have these rolled threads, you actually get the grains to align in the material in a way that makes it a cold worked material. And so these threads are a lot stronger than these cut threads. Okay. So, depending on your application, what's important for you as a machine designer to know is that you have a lot of options, and if you have a critical application, you want to make sure that you are navigating your way to pick the right threads. And there's, you can go find manufacturers and find as much information as you want about these different types of threads and applications. So this is just mainly of interest. How do you make the bolts? Well, usually they're cold formed, okay, with a progressive upsetting process, okay, and progressive forging. So you'll have a material, you'll grab the material, then you'll smash the material with a die that will forge it into an initial shape, and then an intermediate shape, and then the final bolt head shape. This is just some different examples of how different head shapes are made. And you basically are just smashing the metal in, cold working the heads to get it into the shape that you wanted. So that's how they're made. Now, when we talk about these bolts, we need to know how strong they are. And we can't just look up the material properties and use those, because they won't give us the most accurate numbers. Okay, and so bolts are tested to what is called the permanent set, and that is the location where the load causes a permanent deformation in the bolt, and this is slightly less than the yield strength. Okay, so you can't just go up to your material properties and use your yield strength, or you can, but you need to reduce it by a few percentage to get to your proof strength. Okay, in this case here, this is just this is different SAE grades. This is 1 through 8.2. The larger the number, the stronger the bolt is. And you've probably seen those markings on the top of the bolt. Well, you can look down and see what they are. If you have grades 1 through 4, or 1, 2, or 4, then there's no real markings on the top. Okay, so you'd have to get some other information. If you have 5, you have these 3 ticks. 5.2, 3 ticks close together. 7, you have 5 ticks. 8, you have 6 ticks. 8.2, you have 6 ticks, but they're all spaced close together. Don't ask me why these are shaped the way they are. I have no idea. But you can look at the top of the head, and then you can actually look up that SAE grade of bolt, and then you can go and get your proof strength. Okay, this is the strength that we care about, and that's what we'll design against. This is the different way these materials have been made. These are low carbons for the lower strength, medium carbons for the higher strength, and then the highest strength they're quenched and tempered, and they have a different grain structure. Okay, so these 0.2 and 0.8, these have martensite here, and they give you a little bit higher strength for that grade. Obviously, the higher grade is, the more expensive they are. And we have another equivalent or analogous strength rating for metric sizes. They go from 4.6 to 12.9, and they are all stamped on the top. So you could look at the top. If you have a bolt that has a 5.8, don't try to screw it into a US thread, okay? Because you got a metric bolt. So if you got numbers on the top, you got a metric bolt. If you got ticks on the top, then you got an SAE bolt in general. So that is all we have for the introduction to bolts and stresses. So bolts and fasteners, screws and fasteners. So are there any questions? All right, so I don't see any questions, so we'll go ahead and end the lecture now. Just if you have any questions, shoot me an email and let me know. Thanks.